Bismillah ar-Rahman ar-Rahim. We'll continue our class in the CAM design and analysis, and we have stopped here in part 4, which is the CAM design. And in general, we start our CAM design by a specified follower motion curve that we have discussed in the previous class, while we have no CAM yet. So first of all, as I explained in the last class, we need to have the displacement diagram of the follower, the motion of the follower diagram. Then based on that, we will design our CAM profile, which is the CAM itself. So as the CAM profile is the generating surface which produces the output follower motion, the design process will follow a reverse engineer approach. So if we need to design the CAM, we need to imagine how the follower will move based on the curve that we want. Then based on the movement of the follower, we will draw our CAM design, and we will have, our CAM profile, and then we will have our CAM that will generate a force that will let the follower move based on the diagram that we put in the beginning. So that is, we rotate the follower, as I said, relative to the CAM, while forcing the follower to follow a contour compatible with the specified displacement diagram. So here, as we see here in this example, so this is the CAM profile, which is the dark black line, and here we have a roller follower. So we will imagine this roller will move in this part, then this part, as well as this part, as here drawn, until we reach this point. And the touched point here, or the tangent points, will give me the profile of the CAM. So we'll discuss what I explained in the last lecture what we meant by the base circle. So the base circle, which is this circle, it will give me a circle that its radius is the minimum distance between the CAM center and the tangent point, or the touch point between the follower and the CAM. And we have, as we see here in this example, this is the displacement diagram, and based on this displacement diagram, as example here, the first point, which is this much distance, assume this method as example 1 millimeter. So once I have the base circle, which is this base circle, and the distance in the first position, which is 1, assuming this is the follower, as we said, we need to imagine the follower moves as the dashed line here, 1, 2, 3 until 11. So in the first step, the head of the follower, this point, the distance between this point and the base circle should be the same distance of this one in the displacement diagram. We'll discuss this inshallah further in an example later on. And this is another example that shows us a ruler follower, and it will and it explains the same concept that I have explained before. As example, in part number 6, this much distance should be increased as here, where our base circle, this is our base circle. So the distance from the base circle and here will give me the center. Will give me the distance as mentioned here in the displacement diagram. We'll see this inshallah further in different examples. As we see here, we need to imagine that the follower will move around the CAM profile. The difference here, we have an offset CAM follower. So this is another approach that we will discuss later on in a complete example, how we can deal with the offset and the difference between the CAM normal inline CAM design and the offset CAM design. So this is another example that shows us an inline flat follower cam, and as I said, it could be moved clockwise or counterclockwise. Here it's clockwise, which is the position, first position, second position, and so on. Here it shows us the displacement diagram with the equations that we have discussed last time. This is a simple harmonic motion, and this is S equal h/2 multiplied 1 minus cosine pi over alpha r multiplied theta. And here we have a dwell, and in the fall we have different equations as we have discussed in the last lecture. So, and after that we can derive the the displacement diagram to have the velocity diagram, then we can derive it again to have the acceleration diagram. And this slide shows us the cam or the displacement diagram and how we can reflect it later on to have the profile of our cam. We'll discuss further, inshallah, this example in details later on. Here we have another example that tell me I have a rise based on self-periodic harmonic motion, and then I have a dwell for 1/8 of the distance. Then I have a parabolic motion here, another rise parabolic motion, and then at the end I have one fall following simple harmonic motion as mentioned here in this example. So it could be rising dwell then fall, or it could be rising dwell then another rising then dwell, and after that it has a fall to compensate the two rises previously. So this diagram will give me, if we convert it to a cam profile, as we are seeing here in the left side, this is the cam profile, which is the black one, and this represents the displacement diagram of the right side of the picture. So let us just define different things before we start. This is what we call the trace point. The trace point, which is the point which is the center of our follower ruler. So this point, it will trace later on what they call it pitch curve, and this pitch curve will represent for us the cam profile. If I have a knife edge follower, that means the trace point, it will be the touch point between the follower and the cam profile. Another thing that we call it pitch curve, the pitch curve, which is the curve that the trace point move along with the cam. So this dashed line, which represent the center of the ruler of the follower once it moves on the cam profile, will give me what we call it pitch curve. Prime circle, which is this prime circle, which is this the dashed one here, and this circle, it has the radius between the center of the cam here, the distance, the radius represent the distance between the center of the cam and the center of the ruler. So just we just draw a circle using this radius. It will give me what we call it a prime circle. After that, the base circle, as I discussed it last time in the last lecture, which represent the circle that it has a radius equal to the distance between the center of the cam and the touch point between the follower and the cam profile. So this is just another example to show us the different circles that we have discussed before 1 minute, and this shows us again what we have discussed in the last lecture, the pressure angle, and we said we need to maximize the F tangent here based on phi, and it should be not exceed phi, should not be exceed 30 degrees as recommended. And you can just reduce the pressure angle or playing with the pressure angle by increasing the diameter of the base circle, or decrease the total rise of the follower, or increase the amount of cam rotation for a given follower displacement, or change the type of the follower motion, constant velocity, simple harmonic motion, or parabolic, or you can change the amount of the follower offset. You can follow those 5 to just change the amount of phi that you want to decrease it less than 30, so you will have more force that's generated from the cam to the follower. So let us just start after we discussed the concepts behind the cam. The first example, as we said, we have different type of cam follower. In our lecture today, we will discuss two examples. One is will be inline cam follower, and the follower will be ruler. And in the second example will be offset, and the follower will be knife edge. So here we will just cover all the types, and we will discuss simple harmonic motion, uniform acceleration, uniform velocity, as well as through the displacement rate. So let us just go step by step for this example. So we have here a cam profile. We need to design a cam profile for a ruler follower. So the following data relate to a cam profile in which the follower moves with, firstly, simple harmonic motion during the lift, which is the outstroke, which is the rise, and returning with uniform acceleration. So what's its return, or in the descent period, we will have a uniform acceleration, or what we call it retardation. So we have different data, which is the minimum radius of the cam. So the minimum radius of the cam is 30 millimeter. The ruler radius, because we have a ruler follower, is equal 10 millimeter. The lift of the follower will be 45 millimeter, which is actually h, which is the maximum displacement that the follower will rise through the rotation of the cam. The angle of ascent is equal 70 degree, and this angle, it's from 0, as we have discussed in the last lecture, to beta. So beta is actually 70 degree. The angle of descent, which is the period of 120 degree, we'll discuss it later on, and the angle of dwell between ascent and descent equal 45 degrees. That's mean here we have rise, dwell, then fall, or ascent, dwell, then descent. So here we need to draw a profile, or the profile of the cam, when the axis of the follower passes through the axis of the cam, which means it's an inline cam follower. So just to recap what we have said in the example, theta outstroke, or the rise, equals 70 degree, and the motion will be simple harmonic motion. So we will put S double S double H double N, and then the return period, or the descent, we will call it theta R 120 degree, and the motion will be uniform acceleration or retardation, and the cam minimum, or the minimum radius of the cam, equal 30 millimeter. The ruler radius is 10 millimeter, and the lift, which is the stroke or the maximum displacement that the follower rise, equal 45 millimeter, and the theta of the dwell equal 45 degree. And the type of the follower is ruler, and the system is inline, so it's inline cam. So let us start. So I have my data here in the right corner, or upper right corner, that the one that we have discussed. And first step, we need to draw our displacement diagram. And as we said before, based on the displacement diagram, we will design our cam, or the cam profile. So first of all, I need to put an X line, which is our theta, and Y line, which is our displacement S. And this line represents the maximum lift, or the stroke of the follower, which is 45 millimeter. Here we need to agree, once you draw something, you need to have your own scale. Here we have 45 millimeter, that means 4.5 centimeter, which is appropriate for our design. But if it's, مثلا as example, 15 millimeter centimeter or 20 centimeter, you need to have your own scale. As well as the same thing for the degree. Here we have 70 degree. Once we draw something, we need to represent every 10 degrees by centimeter, or 1 degree by 1 millimeter. So first of all, here we will draw a circle or half circle, and its radius equal 45/2, or the diameter will be, it's the same of the stroke. Why? We will discuss it later on, because we need to draw what we call it simple harmonic motion through the left period or outstroke period. So this much amount will represent it by 70 millimeter, which will be equal 70 degree. As I said, every 1 degree will represent it by 1 millimeter. So our scale will be 1 degree equal 1 millimeter. And this is our first period. And we will draw here somehow our first period of displacement diagram based on what we call it simple harmonic motion. How we will do that? So first of all, I need to divide, this is what we always follow, I need to divide this circle to 6 pieces. So if I have this half circle 180 degree, that means every piece will be 30 degree, and based on the picture as we see in here, every 30 degree I will put a line, then I need to put a dot between those lines, as well as the cross between those lines and the half circle. So, and then after that, once I divided the half circle to 6 pieces, I need to divide this period also to 6 pieces. So here I have 70, so if I divide 70 over 6, so I will find somehow 11 point something, and you can just, using the ruler, put your dots. But engineer-wise, because you cannot divide, you will not have a proper number exactly, because it will has multi-digits, so you will not have a proper division for those 6 pieces, except if you have a distance equal 60, so you will divide over 6. That means every piece will give you 10 millimeter or 10 degrees. But engineer-wise, there is a method called the acute angle, and this acute angle always less than, they are taking it less than 20. Normally they are taking this acute angle 15 degrees. So just draw a line. It has 15 degree with the x-axis or theta axis, and this, on this line, every 1 millimeter or 1 centimeter, put a dot on that. So we will have 6 points starting from here. So this gave me 1 centimeter, and after that 1 centimeter, as well as until find 6 points. From the last point here, I will draw a line from the last point to the last point of 70 degree, right? And after I draw this line, I will make a parallel lines that cross those 6 points, as we see here. This is the first line. This is the parallel other 5 lines of the first line. Once I have those lines, the cross section between those parallel lines with the theta axis will give me a proper 6 divisions or 6 pieces of that line. It's up to you to use the acute angle method, or just use the calculator 70 over 6, and you will have your number. Then using the ruler you can divide the 70 degree to 6 times. So at the end we need to divide this 70 degree, or what we call it 7 centimeter, to 6 pieces. And the next step, which is just, I have 6 dots here on the circle and another 6 dots in the first period, which is the outstroke. So I need to just number those dots from the 0, 0. I have here 0, 0. So we'll start 0, 1 on the circle, then 2, 3, 4, 5, and 6. As well as here 0, my 0 will start, this is 1, 2, 3, 4, 5, and 6 in the outstroke period. Here in the first one, I will raise perpendicular lines with 90 degree, and in the circle I will draw straight lines with 0 degree, as we see here, and the connection between both of every two numbers, here 1 with 1, 2 with 2, and so on, I will mark them red dot. I will connect between those 6 red dots, and it will give me what we call it simple harmonic motion. So you need to follow this procedure to draw this simple harmonic motion. There is another procedure to draw this simple harmonic motion. It's yes. So we discussed in the last class the equation of the displacement, which is S equal whatever for the simple harmonic motion, and it's a function of theta. So just choose different thetas from 0 to 70, مثلا 10 times or 6 times or whatever, and fill it in that equation. It will give you directly S, and you can just draw directly based on the equation the curve. So you have two options, or one thing using the equation and just plug different thetas, you will have your S, or just follow the procedure that I have discussed before, which is the half circle divided to 6 pieces, and your period divided to 6 pieces. Just make a cross lines between those points. It will give you the dotted that will draw for you the simple harmonic motion. The next step, so we finished with the outstroke. The next one, which should be, as we said in the example or in the question, we have rise, dwell, then fall, or outstroke, dwell, then return. So here we have a dwell, and we said the dwell equal 45. So we need to just put 4.5 centimeter here. So this is the dwell, which is theta equal 45 degree. By the way, for the dwell, it's not necessary to be scaled. You can just put it to understand there's a dwell here. So even if it's 90 degree, 9 centimeter, you don't need to draw 9 centimeter. So just draw it with 1 centimeter to show just here we have a dwell. Because the dwell do not have an effect. It's a straight line at the end. So we are drawing here between the last point of the outstroke period and the last point of the dwell a straight line, which is the dwell period. Now we need to just draw the second period, which is the return period or the fall period. And here we are we said it's a uniform acceleration or retardation. And there is a procedure to draw the uniform acceleration, or as I said, there is another approach. Just bring the equation S equal whatever that we have discussed before, and plug different thetas. You will have your S, and just directly you can draw your diagram. If you don't need to just go to that equation, and I have another approach that I can just explain for you, it will be directly just do it directly to have your diagram. So here, just as we use here our scale, it's 1 degree equal 1 millimeter. The same thing here, we are using the same scale for the return stroke, but here we have 120 degrees. Here also we need to divide this to 6 pieces, because 120 divided by 6 it's a 20. So directly using the ruler, we don't need to use the acute angle method. Just divide this to 6 pieces and just numbering it 0, 1, 2, 3, 4, 5. From this side, we need to just look at it from the right side, because it's in the other side of the diagram, not like the first one, which we look at it from the left side. So we need also to make a line in the middle at the third point. And this line we need also to divide it to 6 pieces. So if we need to divide this one to 6 pieces, the distance here, if you remember, it's just 45 millimeter, and it cannot be divided to 6 pieces. It's up to you just to divide 45 over 6. You will have a number with digits, or you can just follow the acute angle as we discussed. Just put in a 15-degree as acute angle and draw a line, and this line divided to 6 pieces using 1 centimeter, 1 centimeter, and so on. And the last one connected, the last point here, the 6th point, connected with the 0 point, and make parallel lines with the other dots. It will cross this line, the vertical line, in 6 pieces, and it will give you a perfect division of those 6 pieces. And then those 6 pieces just shifted to the green line. The most important thing for me, which is the middle line, the green one, just shift those points to the middle line, and then numbering it from down 0, 1, 2, 3 until the last one, which will be 6. Why I am putting the numbers on the left side and here on the right side, it has meaning. We'll see it now. So from 0 point here until here, we need to we need to draw a line that crosses the 3rd point. So this is the first one. Anything is down, we need to connect the 0 with the 1, as well as the 0 with the 2, as well as the 0 with the 3. And from the upper, the last point here, we need to connect it with the 6, as well as with the 5, as well as with the 4. So the last 3 points down, it will be connected from the right side, from the 0, and the last 3 points, which is 4, 5, 6, will be connected with 6 points. So just to memorize it, 6 should be with 6, and 0 should be with 0. And the 3rd line will be in the middle. So now what we need to do later, so we need to draw perpendicular columns or lines from 0, 1, 2, 3, 4, 5, and 6, as we see here. So those 0, it's a 0, so 1, it's very small, then 2, the 3, it's from here till 3. Then I will stop once I cross the line that number 4. Here, if I need to put a line, I will start from 4 until I cross the line number 4. For 5, I will start from 5 until I cross the line of number 5. For 2, the same thing. I need to draw the perpendicular line until I cross number 2. For the 1, I will draw until I cross number 1. So I have points, the crossed point, which is the red one now. This is, if I connect those, here I have 1 here. Let me start from the 0. This is 0, this is 1, 2, 3, 4, 5, 6 points. So if I draw those 6 points together, it will give me what we call it uniform acceleration. So it's very simple, the method. If just I'll go back a little bit with it. So I need to divide 6 points in the theta axis, another 6 points for the green line. I will connect the middle line 3 from 0 until 3 until 6 here with the circle, and those upper points, it will be connected from the last point until the 4, 5, and 6, and the right side from 0 to 1 to 2 to 3, and after that we'll make perpendicular lines from 0 until 6, and if I make a perpendicular from 1, I will stop at line number 1. For 2, I will stop at 2. For 3, I will stop at 3. The same thing for 4, I will stop at 4. For 5, I will stop at 5, and so on. And the crossed point between those lines, it will give me the curve of what we call it uniform acceleration. By this, we end how we can do our displacement diagram, which is the first step. Then the second step, we need to move with designing our cam. One last thing before I move, the displacement diagram, if we just add up those angles, 70 plus 120, which is 190, and then plus 45, which is 235 degree, but still we have something until 360 degree. So that's mean we have another dwell here until reach the 360 degree. So if I minimize 360 minus 235 degree, it will give me my dwell, which is the last thing, 125 degree. So how we can find the last dwell? The complete theta of the cam is 360 minus 70 minus 120 minus 45 will give me 125 degree for the second dwell. And as I said, the dwell always, it's not necessary to be scaled. Just draw it to show there is a dwell here. Okay. So let us move to the second step. We will keep our displacement diagram aside here, and then we will put our center line of or the shaft position of the cam, our cam. Then we'll move with the first thing. We need to draw what we call it the cam minimum, which is the base circle of our system. The base circle, which is 30 millimeter. Just draw a cam or the circle with 30 millimeter with your scale. After that, you need to draw what we call it a roller radius, which is 10 millimeter, another circle, and be sure that this circle should be aligned in line with the cam design, with the cam shaft. So the center of the cam should be in line with the center of the roller circle. So after that, we will have what we call it a prime circle. The prime circle, it has the radius that equal the distance between the center of my cam and the center of my ruler. So I just use the tool here using the half radius of the circle, then draw the green one. Okay. After that, we are assuming that the cam rotating clockwise. It's up to you, clockwise or counterclockwise, but in this example we'll assume it's a clockwise because it's not mentioned in the example. If it's mentioned, we need to follow that. If it's not mentioned, you can choose whatever you want. If the cam rotate on the right side, which is clockwise, that means the follower will move. We'll imagine the follower that will move vice versa, which is counterclockwise. So the cam will rotate clockwise, that means the follower will keep in its position. But if we imagine the follower that's moved, that means the follower will move counterclockwise. So we'll start with the inline between the two centers, and we'll draw another line counterclockwise with 70 degree. So this is my theta out stroke. As we have another dwell, which is the dwell 45 degrees, so we will draw another line with theta dwell equal 45 degree. The third line, which is the theta of return stroke. So we will draw another line, which is the fourth line, with a theta equal theta r. So we have, as here we are seeing 1, 2, 3, and 4. So here we have 1, 2, 3, and 4 with the same angles. Here we divided the displacement diagram to 6 pieces. Here now we need to divide as well the 70 degree to 6 pieces. The last angle, by the way, it's the second dwell. So here now we will draw 6 lines, as we said in the displacement diagram, the same thing, 6 lines dividing the 70 degree to 6 pieces. So just divide 70 over 6, it will give you the amount of degrees that you need to divide this period. And after that, we need to number it from 0, which is the first line, then 1, 2, 3, up to 6. And after that, we need The dwell, we don't need to do anything in the dwell because we said it's a straight line. That's mean the distance in the sixth line will be the same here, and we'll discuss it later inshallah. But for the other period, which is the return period, also we need to divide it to 6 pieces as we have done in the displacement diagram. Here we have divided it to 6 pieces. And this one 120 degree over 6, which is every 20 degree here. That's mean here we have 20 degree, here we have a 20 degree, and so on. After that, we need to number those lines. As I said, this is 6. As here we know this distance in the first period equal the same distance here in the second period. If you go back to the displacement diagram, this is numbered as 6 and this is numbered as 6. So that's mean this one will be 6, the same thing here will be a 6. So then 6, this will be 5, 4, 3, it's vice versa. 2, 1, and then 0. So we'll start from 0, we'll end from 0. And this is make logic because here we said we have another dwell, right? And this dwell should be 0, 0. And we have here dwell should be the same number, 6, 6. Okay? The second thing, which is we'll start to reflect what we have done in the displacement diagram on our CAM design. So the first period here, it's 0, 0, so there is no distance. We will put our first dot in the 0 place, which is the center of the ruler. After that, we have a distance here of 1. So we will take this distance and we'll draw another point. And this distance, if it's assuming مثلا 2 millimeter or 3 millimeter, it should be the same distance that the system raised from the first point until the point that I need to draw. So the distance between the green circle and the dot red should equal the distance between the profile of the displacement diagram and the theta axis. And we'll move forward until we reach the 6th point. Okay? If I'll move until 6th point here, just let me go a little bit here. And this is the 3rd line until I reach the 6th point. So the 6th point here should be the 6th point here, because here, as we said, this distance, much distance, equal this much distance. And this is number 5 in the second period, right? If you look here, it's number 5. That means this is the distance of number 5. Number 4, the same. This is the distance of number 4 until I reach 0 here. This 0 represents my 0 in the displacement diagram. Okay, and after that, the second step, I need to draw a circles with the radius of the ruler, because here the ruler is moving. So this is those red dots. It represents the center. It represents the center of the ruler. Once I imagine the ruler is moving along the profile. So this is my rulers, the imagination of my ruler. So if I need to connect between the centers, will give me what we called it before pitch circle. So this is my pitch circle. Now, what is the mean of CAM profile now? So if I decrease from the pitch circle, the amount of the radius of the ruler will give me what we call it the CAM profile. Here, how I can draw the CAM profile, I just move my cursor or my pen tangent with those orange circles or with the ruler, as we will see here. So the tangent of those circles will give me what we call it CAM profile or CAM circle. Just one notice, this place of the CAM should be the same radius, as well as here will be the same radius. So the most important thing here, to recap how we will draw our displacement diagram. Once I have my displacement diagram, the reflection to have a cam profile, it's very easy. Just you need to follow the steps that we have mentioned. First of all, you need to draw the the base circle, then draw the ruler or the knife. If it's the knife, we will discuss it in the next example. Then after that, you need to draw your prime circle, which is the distance, the radius, the circle that had radius equal to the distance between the center of the ruler as well as the center of the cam. Then you need to just reflect the distances that you have drawn and the displacement diagram on the circles that we have seen before, the distance from prime circle, which is the green circle here, until I reach the same distance of the displacement diagram on every line from 0 to 6, then from 6 to 0. Then I need to draw my pitch circle, which is the connection between the centers of the rulers, as well as the cam circle, which touch or it will be the tangent of those rulers. And I hope this is just explain in details for how we can design our cam profile. And then just remove everything that we drew as lines, whatever. This is the previous circle that we draw as a ruler, and this is the dot that we draw in the beginning, which is the camshaft. Just to draw here something look like a camshaft, and here the frame that will fix the ruler for me, or the follower for me. So here, as the cam rotate clockwise, as we see here, so the follower will start raise based on the cam profile, which will give me a logic here. If we look to the displacement diagram, here I have a dwell, and there I have a fall or return. Then here we have another dwell. So by this we complete the first example, which is the cam profile for ruler follower. Then we need to discuss another example. Here we will discuss a knife edge, but not inline cam follower design, but it will be an offset. And there is just small difference between both of them. We'll discuss it later on. Let us just discuss deeply the example here. A cam is to give the following motion to a knife edge follower. So first of all, we have a knife edge. The outstroke is 60 degree of cam rotation. I have a dwell 30 degree, then return stroke for 60 degree. Then I have at the end a dwell. If I just 30, 60 degree minus 60 minus 30 minus 60, it will give me 210 degrees. So the stroke of the follower is 40 millimeters. So the maximum distance of the follower will give me 40 millimeter, and minimum radius of the cam, which is the base circle, equal 30 millimeter. Follower moves with uniform velocity during both outstroke and return stroke. So for both, for the raise and the fall, or the outstroke and the return, we will follow what we call it uniform motion or constant velocity. So we need to draw the profile of the cam when the axis of the follower offset by 20 millimeter from the cam shaft axis. So here, just to summarize, theta outstroke equals 60 degree uniform velocity, theta of return equals 60 uniform velocity, first dwell 30, the second is 210, the minimum cam circle, which is the base circle, 30 millimeter, the left, which is 40 millimeter, and the type is knife edge, and we have an offset of 20 millimeter. As previous, we need to draw our x-axis theta, and y-axis is s, and the last line, which is give me the maximum left stroke, which is 40 millimeter, and I need to divide my area to 4, which is the first outstroke, which is 60 degree, then the dwell, which is 30 degree, after that the return stroke, which is 60 degree, and the last one, which is a dwell, which is 210 degree. As I said, the dwell, it's not necessary to be scaled. But for the outstroke and the return, as well as the stroke here, it should be scaled. Okay, if it's here 40, if I need to divide over 6, as I said, we can use the ruler or the calculator and the ruler or the acute angle, and we put 15 degree divided to 6 pieces every 1 centimeter, and the last point we connect it to the here. Then paralleling, crossing those points will give me 6 pieces here. The same thing, I need to divide it here because I will use it later on. After that, I need to divide this period to 6 pieces, as well as the return stroke to 6 pieces, and I can number then. This is 0, 1, 2, 3, 4, 6, and on the x-axis 0, 1, 2, 3, 4, 6. And the simplest diagram, which is the uniform velocity, it's a linear, so just will cross between those ones, and here we forgot here from 0 to 6. After that, just make horizontal lines and perpendicular lines, and the crossed between those lines on the outstroke as well as the return stroke will give me the displacement diagram. So this is my displacement diagram. On the dwell it will be straight, and on the return stroke also it's a uniform velocity. It's very simple in the uniform velocity, not like the one that we have discussed in the previous example, which is the simple harmonic motion or the constant acceleration. At the end, if you don't need to follow these procedures that I have explained here, now just go directly to the equation, fill the thetas that you want. And as example, here in the outstroke, I can fill 10 values of theta from 0 to 60, and in the equation of S for the uniform velocity, and I will figure out 10 values of S. Then the cross between those two values, it will draw for me the diagram of uniform velocity in the outstroke period, the same thing in the return stroke period. So now I need to connect between those red dots as well as here for the dwell to have my displacement diagram. Very simple. So this is my displacement diagram, and we are finishing. We have finished now the first step, so we need to move to the second step, which is the cam profile. So first of all, we need to put our center, and we will draw the minimum cam circle, which is the base circle with 30 millimeter radius. And after that, we have here the difference. We have the offset. So if I have an offset, I need to draw an offset to the right or the left side. It depends on the question, or it depends on you if it's not mentioned. In this example, we'll follow the right offset, so that means I need to draw another line parallel to the vertical line, but it's far away at 20 millimeter. And after that, I need to draw a circle, and this circle, it has a radius that equal the distance between this center and the new green dashed line here after the offset. So this is what we call it offset circle. And this offset circle, it's different from a previous example, and we will depend on this circle to draw our cam profile. And now we will assume our cam will rotate clockwise. That means we need to imagine that the follower will move in the left side or counter-clockwise. First of all, I need to make a dot between the point that crossed between the offset line as well as the base circle. Then I need to draw a line between the center of the cam or the center of the base circle and this black point. And this is my reference that we will use later on. So from this reference, I will draw the first 60 degree of outer stroke period. This is what we call theta 0. And then I need to divide this period to 6 pieces. And every period, it will be or every piece will be 10 degree, and after that I will mark the crossed point between the offset circle and those lines. As I said, my reference always will be the offset circle, not the like the one before, which was the prime circle. So from those points, I need to draw a lines, and those lines should be tangent the offset circle in every line. As example, in line or in point number 0, we will draw a tangent line to the offset circle at that point, which is 0, and we will name this line 0. The same thing for 1, the same thing at 2, the same thing and 3 and 4, 5 and 6. This line should be tangent to the offset circle at that point, and we named it 0, 1, 2, 3 until 6 as mentioned before. Now, the second step, which is our dwell, the first dwell, it will be 30 degree, and we will draw a line at 30 degree, which will give me my dwell, and we will put a point called 6, because I said in the dwell, once I reach a dwell and I will move through the dwell, we will keep our naming of points or lines, or the distance itself, it will be the same. So here it will be the same 6, because it's the same point. There's no change from this 6 to 6. And as same, we will draw a tangent line crossing this 6 point, and we name it also 6. After that, which is the return period, we have 60 degree. We'll draw an angle also with 60 degree, and this 60 degree will be divided to 6 times by 10 degrees. And the last angle, which is the last dwell, we'll discuss it later on. In the return period, we will divide it again to 6 pieces, or 6 times, and every time it will has 10 degrees. And the points that cross between those lines and the offset circle will mark them, and we started from the dwell by 6. We'll go back down until reach 0, because we said once I reach here 0 and I have a dwell, it should be the same 0 once I started. So again, we'll make another lines tangent to those points, starting from the 6 that we have done in the dwell, then 5, then 4, 3, 2, 1, and 0. So by this point, we are drawing here. We have drew the lines. We need to go back to the displacement diagram, and based on the displacement diagram, there are distances based on the motion of the follower. As example here, in the first point, we have this much of distance, right? We need to reflect this distance on the line that we draw from 0 to 6, then from 6 to 0. So now we will start to take the distance between the base circle or the prime circle if it is ruler. Here we have the knife, that means we have just only the base circle, because in the knife edge follower, the prime circle and the base circle is the same. So the distance between the base circle and the line number 1 should be equal this distance. So those two distances should be equal. And the same for 2 and 3 and 4 and so on until finish all of them. So this is point number 2, 3, 4, 5, 6. And 6 should be here the same 6, then 5, 4, 3, 2 in the return stroke, and 0. 0 should be touch the base circle, or else will be our solutions will be wrong. So we will start from the base circle. We need to return to the base circle. As in the previous example, we started from the prime circle and we finished with the prime circle. So if I just draw a line between those points, it will give me my cam profile. If it's a ruler, it will draw for me what? the pitch circle. But here in the knife edge follower, the pitch circle and the cam profile or the cam circle, it's the same. So by this we reach to our cam profile. We are drawing here the knife edge which has an offset between the cam shaft or the center of the cam and the knife equal 20 millimeters. So we summarize this our displacement diagram, and this based on this displacement diagram we draw the line, the points, the red points, and then we draw our cam profile, and this is our cam shaft which is in the center of the cam profile, and this is our knife. And I hope you understood what we have discussed in those two examples, and I encourage you to look at the slides again, as well as Dr. Khalif note, as well as the book, and revise this video. In addition to that, just as you see here in this slide, which is in the slide that I will upload through the Blackboard, I'm encouraging you just to look at those videos. You will have more understanding. And actually, in this lecture, we have discussed what we call it offset knife follower and cam profile for roller follower in the previous example. For this one, we didn't discuss it. For this one, we didn't discuss it. Just look at those videos. And I believe this one, it has something wrong. Just be careful once you see these videos, because he didn't follow the offset circle. He should follow the offset circle. He made it by mistake. So please just be careful once you see this video to be sure that he did a mistake, and once he didn't follow the offset circle. He should follow offset circle. But just look at this example to understand how he deal with the offset once we have a ruler. Okay. So good luck, and thank you so much to hear this video. So just as I said, follow the book and Dr. Khalif notes, as well as my slides, and we will have an online session inshallah for Q&A. And if you have any question, any misunderstanding, just write it down once you see this video as well as the other videos, and put them so you cannot forget, and we'll discuss it inshallah later on. Have a nice day, and please, just as I said, down your notes, and we will discuss it on the online. Thank you so much, and Assalamu alaikum.